on the topic of stability, the last topic for this course, process control. So let's consider a particular third order system in which the schematic diagram of the block diagram will be shown here. So for this particular system, you have the controlled variable C, and you have the transfer function of the process here. So we could see that your process is a second order uh, process because its transfer function is already second degree in the denominator for S. And this is the sensing instrument, which has the transfer function, which is that of a first order system also. You have this load U. Okay, this is just a review, and this represents any of the input variables that will affect the value of the control variable. And you have here the K sub C as the transfer function of your controller. The error that you see here is the difference between the set value and the sensed value of your sensing instrument. Okay, so this is for our block diagram for this particular third order system. Now, the expression, let's say for that system, for a step change in R, meaning we keep U constant, just like my discussion last Monday. So for a system that is subjected to two types of disturbances, one that could be in the form of the loads or any of the controlled variable, or one that could be in the form of changes in the set point, which is the R. For this system class, the response C for the controlled variable for any change in R means that your U was set constant. So there's no changes in the U. And in this case, that particular response is this. The 1 over S, you know already that this represents the Laplace transform of the input representing a step change in the set point R. So this is supposed to be C over R. And that R we already represented as 1 over S and cross multiplied it here. And that the particular block diagram that you have seen, which has three elements present, I'd like to go back to that. This one, if you're going to write its overall transfer function, you can see that all the transfer function of the elements were multiplied, as you can see here. And last meeting, we also discussed how you're going to derive the transfer function of a particular system based on the algebra of the different variables that appear in the block diagram. So you know that last Monday. So let's say you know that already, and this is the transfer function. This part here is the transfer function, this one, the transfer function, the overall transfer function of your system. And we just simply cross multiplied the representation of the Laplace transform of the step change in R, which is 1 over S. Now, for this system, for example, you will be asked how to determine whether it's going to be stable or unstable, or if the system is stable or unstable if it is subjected to this particular type of disturbance, and that is stated here as step change in R. So before we go to that on how we determine whether it will be stable, probably if you don't have this particular chapter taught to you, what you will do is graph the response of such a system. So if you're going to graph the response, then you are obliged to get the inverse Laplace of this expression. And most of you would probably more than agree with me that that would be very tedious because you will have here to use the method of partial fractions, which will need the three partial fractions on it, and that would be lengthy. Actually, it's not difficult, but that would be very long for you to be able to graph. So the only way that you can graph is you know how to invert this one. Is for you to know how to invert this one. You cannot graph unless you have a C of t. I think you know that. So for different values of K sub C, let's say, for example, you don't know any test that you can perform whether the system will be stable or not. Let's say we fix the tau, the time constant, this time constant, the system, for the time constant of the entire system, let's say we fix it And the same thing, of course, the time constant of each of the elements there in the system will be fixed. Then you will be left with a graph that is dependent on the value of the constant k sub c, which is the gain, the steady state gain of our system, the third order system. So if we are going to plot the equation that you have derived from or out of the method of partial fraction that you have performed on the equation that I have shown to you in the previous slide, this will be the different form of the graphs. So for the lowest value of k sub c, this is the lowest k sub c value, the 3, and then it has been increased up to 12. You will notice that as we increase the k sub c, the degree of oscillation of the response increases. And if you notice, even if it's small, like in this case, you have 3 here, the smallest value that was substituted is 3, you could see that still the ultimate response of your system is having an offset. It should have been rested here on the 1 because it's a step change in the input. But if you notice in this case, it's not resting on the 1. So in this case, with a small value for k sub c, you have an offset. The degree in which your steady state, your new steady state value has deviated from the original steady state value. Whereas for the rest, even though there's much oscillation, they will be rested on the original steady state value. This would be difficult if you don't have, let's say, a software that can do the graphing for you. If you'll do it in pure hand calculation. So there has to be an alternative that you can do rather than invert the equation that has been provided. So that particular process is what we call as the test for stability, which does not require you to invert and graph the response equations, just like what you see in here. Now, before we do the test, because the test is very easy, let's define as fundamental what's the stability, or how we define that a linear system is stable. So a stable system is said to be having bounded output for all bounded inputs. So there has to be a certain range in which the output of the system is expected to show. So it says here the output is bounded for all bounded inputs. Then we will ask ourselves what will we consider as a bounded input in terms of the different inputs that you have learned already. So the bounded inputs are those that, of course, will fall within a certain range of value or bounds for a course of time. So example stated here is the step function and the sinusoidal function. These two functions does not grow over time, does not decrease over time. They are just steady in terms of magnitude. Whereas the unbounded input that is given here as an example is the ramp function. This one, as shown in the graph of a line, will increase, of course, indefinitely based on the slope of that particular line, or it will decrease depending on the slope of that particular line as well. So if your system is subjected to these two bounded inputs, it is expected to have to show also a bounded output. If its output is bounded or is displaying a value that is within a certain range, then it is said to be unstable. Otherwise, that system is said to be unstable. Now, if a system is said to be unstable, there is this what we call a condition of saturation. Okay, it's just but an emphasis on each of the bullets in this slide. So when is that particular system that is unstable uh, reaching a period of saturation? So a physical system which is unstable will not follow the response of its linear mathematical model, and that is the equation that you have derived from the method of partial fractions, and it will go beyond the physical bonds. If that is the case, the system is said to be saturated already. Now, this is not so comprehensible if we'll just speak of the math and when we just speak of the statement itself when we speak of saturate. So, as an example, for a linear valve, which is a final control element, the most common final control element that is being used in the process, no matter how you change the pressure in the diaphragm of that particular pneumatic final control element, you you either increase it or decrease, you won't see any changes anymore in the flow that is being controlled, or let's say being set by the valve, because it has reached already a condition which is saturation. So no matter how you increase the pressure, there won't be any changes in the flow because the valve is already, shall we say, the system that is flowing through the valve is said to be saturated. Now, having said this and having defined the linear, rather the stable and the unstable system, and when the unstable system reach a condition of saturation, we will go now to how we're going to do the test. And there is this particular stability criterion that is outlined in our, of course, the only textbook that we are using by Kauhanar. Now, what is this particular stability criterion? So let's say, for example, you're given this system. Even if you do not know the Routh test, which I will be discussing in the next slide, you would still be able more or less have an idea whether your system will be stable or not. That is based on its roots, the roots of the characteristic equation. What is the characteristic equation? I think I have not written it here. It is simply the overall transfer function of your system added to 1 and equated to 0. That's your characteristic equation. So 1 plus the overall transfer function of your system being equated to 0, the corresponding polynomial yielded by that sum of 1 and the overall transfer function of your system will be your what we call characteristic equation. If it is linear and you won't have any problem with using factoring, then right away you'll be able to tell whether your system will be stable or not. If you will yield real roots for such factoring that you do based on your characteristic equation, automatically your system is already unstable. Again, if you have your characteristic equation and you have done factoring, or probably if it's nonlinear and you cannot have it factored using the simple factoring tool in algebra, but still you're able to find the factors or the zeros of that particular polynomial, and there's a real value that is yielded, automatically your system is unstable. It's already unstable. There's no need for you to do successive, let's say, validation tests like the Routh criterion test. Okay? But nonetheless, there's an alternative for you to use, which is just based on a process comparable to that of a determinant. You just use the sum of the products of the terms that you will later on place in the form of a table, or just say in the form of columns. And then out of the values that you will be producing on the first column, then you can tell whether your system is stable or not. So nonetheless, even if you don't know Routh criterion, and now I'm telling you, you can still find whether the system is stable or not. But in the case of cross process control class, it's not just as simple as saying, okay, tell me whether the system will be stable or not, and this is the transfer function of the system. You know that is not as simple as that, although it could be as basic and as simple as that. What do I mean by that? It's because if you have thoroughly read what is in Kauhanar, there are problems that ask you for the value of the K sub C. If you have recalled my discussion in the second slide about how the K sub C plays a very important role on whether the system will be stable or not. So you will be asked by some problems to determine the range of value of that particular K sub C so that your system will be stable. And if that is the case, then a simple factoring will not work already, because this time it is the system that is already stating that I want myself to be stable, tell me what would be the corresponding value of my gain, that is the K sub C. That way, I will be steady, or that I will be stable specifically. Then, this is the time for you to really know the Routh test. Otherwise, you won't be able to answer such a problem because you are only limited to determining the roots. That way, you can find whether your system will be stable or not. So it is really then very important that aside from knowing the roots of your characteristic equation, you still know how to perform the Routh criterion. Because in that particular table, you will later on see the appearance of the K sub C. And upon equating values, you will know what would be the range of values in which your system will be stable for that K sub C. Okay, so what is this particular Routh test? Let's say, for example, for the system that we have in here, you have your controller, you have your process, and this is your sensing device. You are given these transfer functions. So this is for the proportional integral controller. And for your process, your steered tank heater, this is a transfer function. And for your sensing device, without the log, this is the transfer function, a simple constant. So these are the transfer functions of the block that was shown to you in the previous slide. Using this, then we will come up with a characteristic equation which we can apply the Routh test. Now, what is this Routh test for stability? So it's an algebraic method of determining how many of the roots of the characteristic equation have positive real parts. Now, I'd like to explain this one. Why positive real parts? If you did the factoring that I mentioned a while ago and you're okay because none of your roots are real, then you're saying, okay, my system could be stable because none of my roots are real. But the thing is, even if all your roots are complex, what do we mean with complex root? A root that has a real part and an imaginary part. You've learned that in advanced math that whenever your, shall I say, your quadratic equation does not yield real numbers, the answers that it might give you are in the form of pairs of imaginary numbers, or what we call conjugate complex pairs. A complex number is said to be complex because it has a real part and an imaginary part. What's the real part? For example, you have 2 plus I. That's a complex number. The real part is 2, the imaginary part is I. So the sum of the two is said to be a complex number. So it's stated here in the first bullet that even if you're happy already, for example, since after you have done the factoring of your characteristic equation, there was no root that is real, oh, my roots are all complex, then you shouldn't be happy when the real parts of your complex roots are positive. Meaning, even though you have already yielded complex roots, let's say 2 plus I, that 2 is positive. It's a positive real part for that particular complex roots. When that is the case, your system is already unstable because the roots have to have negative real parts in that case. In this particular Routh test for stability. If there are no roots with positive real parts, the system is stable. So take note again, you should not have roots that have positive real parts. Your complex roots should have negative real parts, like negative 1 minus I. That your system will be stable if that is the case. But 1 minus I, it makes already your system unstable. Okay? The test is limited to systems with polynomial characteristic equation. Cannot be used to determine the stability of systems with transportation lag. Now, what is a transportation lag? If you recall, that's a system, or that's a system for, let's say, a fluid flowing through a pipe. And that is the only system so far that we have discussed in which the transfer function is e raised to minus s tau, for example. It's the only transfer function that is exponential. So if you will not change that particular original transportation log to an approximation like the Taylor's approximation, or the first order per day approximation, or the second order per day approximation, you will not yield a characteristic equation that is purely polynomial without any other function except, let's say, variables raised to a particular exponent. You will have the appearance of the exponential function. If that is the case, the Routh criterion cannot be used, or the Routh test cannot be used. It can only be used if you change your transportation log into any of those approximations that I have mentioned, which you also learned. There are 3 approximations for that. Taylor's, the first order per day, and the second order per day. So you just have to choose. Then you're good to go. You can already test for stability of that system which has a transportation log which you approximated. So based on your decision on what you will use as an approximation. So take note of these things which the Routh test already lays in the first place for you to know. If any of the coefficients of the characteristic equation is negative, the system is definitely unstable. And the Routh test is not to be, shall I say, performed anymore. So if you have, for example, 2s squared minus s plus 1, the coefficient of negative 1 in the s term already tells you that your system is already unstable. There's no need for you to do the test if that is the case. And there's no need for you to perform the factoring that I have mentioned a while ago to test whether you have roots which are real, because automatically it's already unstable. The next bullet here, this is the final bullet that tells you when you will apply the Routh test. If all the coefficients of the characteristic equation are positive, the system may be stable or unstable, and the test for stability has to be done. So if you're going to ask me, what is very important is this: if all the coefficients of your characteristic equation are positive, it's still possible that your system would still be unstable. So you cannot even conclude that even if all the terms in your characteristic equation are positive, your system is already stable. Since you're not certain and it's not yet certain, then that's the time that you will perform the Routh test. So this tells you that you can already perform the Routh test for stability. So it's all anchored upon the characteristic equation. Okay? Now, any questions so far? Okay, so we will proceed. The Routh array is something like this. If you have your characteristic equation class, say for example, 2s squared plus s plus 1. Okay, your AO there is 2. So the first coefficient is AO. And of course, the next would be A1, and then you have A2. So the way you write it here in the Routh table, we call this the Routh table, is alternating in terms of the coefficients of your terms that appear in your characteristic equation. This is the coefficient of the first term. This is for the second. This is for the third. This is for the fourth, and so on and so forth. Now, this B1 and C1 and D1 and E1 and F1, same thing with this, the rest of the elements here in this table are to be computed based on the following formula. So for you to complete your Routh array, you have this formula, and it has actually a pattern. A1, A2 minus AO, A3. I'd like to go back. So A1, A2 minus AO, A3 divided by A1. That would be your B1. Okay, it's just like you're doing determinants. A1, A2 product minus AO, A3 product divided by A1, that would be B1. If you have class, for example, a polynomial which has only 3 terms, then there's no need for you to complete everything here. You stop here in B1. And what tells you whether your system is stable or not? So your system is stable if all the elements of the first column of the array are positive and non-zero. Then you are certain that it's already stable. So all these elements here should be positive and non-zero. So if you have all positive elements here but you have a zero in the last element or on any of the elements, your system is still unstable according to this particular test. Now, the other formulas in determining, let's say, B2, C1, and C2 for longer polynomials for your characteristic equation are written in here. So it's still using the same pattern. B1A3, for example, where is that? B1A3 minus A1B2 divided by B1 is C1. So always you start with the element on top to get the element below. So B1A3 minus A1B2 divided by B1, it's always B1. In this case here, it's always A1 for this, is equal to C1. You don't need to solve for this unless you need it here. You don't need to solve for the second column until you need any of the elements here. Okay? And that's it. All you have to do is make sure that the first column elements here are all positive and non-zero. Otherwise, then it is already unstable. Okay? And I think this is where I'm going to end with this particular set of slides for the stability of any system. So remember the table, remember the formula in completing the elements in the table. Excuse me, can you please mute yourselves? Somebody's microphone is unmuted. Okay, so you just need to follow this formula so that you get to complete your table. And that's it. But nonetheless, class, when you complete your table, just like the scenario that I have mentioned a while ago, it could be that your K will be present on any of the elements here in your table, and you would be asked what particular value of K will make the system stable. You just have to answer a simple question, and that is the value of that K, or specifically that K sub C, should make this particular element, for example, real and positive, should make this particular element real and positive. Otherwise, then it will make any of the elements in my first column real but negative, or it can make it zero. That will make my system now unstable. There are, if I'm not mistaken, there are around 3 or 4 sample problems in Kauhanor which you can read, starting from the very basic down to the part which asks for the K sub C value. So please check on what's available in your book. I'm sure you have soft copies of Kauhanor also. Okay? This ends this slide. So we will have a short meeting this afternoon because I think we still have around 13 minutes. So if you have any questions, I will now stop recording.